Hello, everybody. We are going to now look at an introduction to numerical differential equations. And in particular, these are going to be ordinary differential equations because they contain just ordinary derivatives like you would see from introductory calculus. So this is part of your numerical analysis class. You've already done quite a lot so far, but now we've gotten to the point where we're going to look at these initial value problems, which is I've got some x prime equals f of t and x. So this is the typical setup for a regular first order differential equation. And I have some initial values. So at time 0, I have something going on. And we're looking for the function x of t. Now, when you took a differential equations class, or maybe you're taking one right now, you studied techniques like separation of variables, undetermined coefficients, Laplace transforms, all these other techniques to find the function x of t that actually does the job. A numerical solution says, forget it, I'm not going to find the algebraic form of the function. What I'm going to do is I'm going to take a whole bunch of discrete times, so time 0, time 0.1, 0.2, 0.3, something like that. And at each one of those times, I'm going to get an approximation for what the solution is. So say at time 0, I know the time, or I know the solution. At time 0.1, well, I've got a guess. At time 0.2, I've got another guess. At time 0.3, I've got another guess. And then you can piece all of those guesses together and you get yourself a plot of what the solution would look like. So the goal in numerical ordinary differential equations, numerical ODEs, is to build fast and stable algorithms that will do this approximation for us. And then we want to actually have the analysis to be able to say how good is our approximation. So in this introductory video, I just want us to look at a kind of somewhat typical differential equation, right? So I've got x prime equals sine of x squared plus t. And stop and think, is there any way you would do this by hand? Because if you can solve this problem by hand and get an analytic solution, there's really no need whatsoever to go find the numerical solution unless the by hand technique is so horribly cumbersome that you would never want to do it actually. But in this particular case, there is going to be no by hand technique to actually solve this thing. So here's what I've done. And as you've seen in all of these other videos, you can ignore the code that I've written. I'm just going to scroll past it. I've got the exact solution here in red. Let me zoom out just a little bit. There we go. I've got the exact solution to this thing in red. Don't worry right now about how I found it. I found it. Right? And then I said, let's take 5 points and make approximations. And I've got two different techniques, my blue technique and my black technique. The blue dotted technique, 5 points. I've got, there's 1, 2, and it's hard to tell, but it looks like I'm drawing straight lines in between these guys, right? Because that's all we can do. I've got an approximation, another approximation here, another approximation somewhere in here, another one over here, and I'm just drawing straight lines in between them. And the black approximation does the same thing. And both of them are horrible. They miss the exact solution completely. So 5 points was kind of the bad idea. Okay, what if we take 10 points to make my approximation? Okay, now the black solution actually does pretty darn well, and it kind of loses it over here and just kind of goes off the rails. And the blue doesn't do quite as well, and maybe it's actually a little bit better over here. But it's a little bit better, at least initially. Okay, 20 points. So I've taken my interval from 0 to 3, split it into 20 equal slices, made an approximation to the solution, and check this out. The black, you can hardly even tell the difference until it starts to stray over here. The blue is still not doing quite as well. And again, you notice that we're putting a point, we're making an approximation in each one of the points and then drawing straight lines in between. You can actually still see that these are straight line segments in between my approximations. What if I did 50? Well, now at 50, you can't even tell that the black solution's missing the exact solution until almost right up here. And the blue is still missing pretty badly. So it looks to me like approximation method number 2, my black solution here, is actually doing great. At 100 points of approximation, the black solution, you can't even tell that it's there. It's right underneath the exact solution. And the blue is still missing a little bit. And if I go further, both of them are just doing stellar. It's hard to even tell that there was a difference. At 1,000, you can't tell whatsoever. This is going to be what we do for all of our techniques for initial value problems. We set up some way of approximating the solution at discrete time points, And then we have to have some analysis to say, how good is this actually going to be if I take 50 points versus 100 points versus 1,000 points? And really, that's a question of how much computation time do I want to give to the computer in order to get a solution that's as accurate as I really want? Do I really need to run 1,000 iterations, or can I get away with 100? Okay, we're going to do lots of different techniques for numerical ODEs. That's going to be the flavor of all of them. See you in the next video.